Let's talk about graphing rational functions. When we look at graphing rational functions, we have to consider that they have points of discontinuity, which means there are places on the graph that they actually don't exist. We have asymptotes, which are lines in space that a graph gets closer and closer to but will never touch. They're vertical asymptotes. In order to find vertical asymptotes, and we're going to abbreviate those on the next boards as V dot A dot, so it's like VA stands for vertical asymptote. You set the denominator equal to 0 and you solve. So just like when we were solving by factoring, for instance, if our denominator is x minus 3, x equals 3 would be our vertical asymptote. But we'll look at some examples. For horizontal asymptotes, you compare the degree in your numerator to the degree in the denominator. So I set up a generic example where a and b are our leading coefficients of the numerator and the denominator. The degree of the numerator here is n, and the degree of the denominator is m. So in other words, if the degree in your numerator is less than the degree in the denominator, your horizontal asymptote is automatically y equals 0, which is the x-axis. This occurs most often. A lot of times our degree in the denominator will be bigger. But then these other two can happen as well. If your degrees are equal to each other, then you say the horizontal asymptote is this number over that number. So if it's 1 over 2, if it's 1 over 1, it's whatever those numbers are. So you just set that up as y equals a over b and whichever numbers are there. And then if your numerator, the degree in your numerator is bigger than the degree in the denominator, so n is greater than m, there's no horizontal asymptote, because in that case you could actually divide it and it would not be a rational function anymore. And we'll look at one like that. And then there are holes. So when we talk about points of discontinuity, we think about asymptotes. There's a vertical, there's horizontal, and there sometimes can be more than one vertical. And then there are holes, and there could be more than one hole, but sometimes there's just one, and sometimes there's none. These occur where you have a common factor that cancels out of your numerator and denominator. So for example, if you have x minus 3 that cancels out, then you have a hole at x equals 3. Let's look at some examples of these. So for finding points of discontinuity, if that's all we're asked to do, they're talking about holes and the asymptotes. I put them in this order on purpose because it's easiest to look at your holes first, because if there are any holes, you want to rewrite the function so that it's more simplified before you pick out your vertical asymptote. And then you can always compare for your horizontal asymptote. I just like to use the original function. All right, so let's look at example 1. I have x over x squared minus 1. So I could start by factoring the denominator out. It's always good to factor first, just like we have in the rest of this unit. So now I see that nothing would cancel out between x and the denominator, so I have no holes. I'm just going to write none. So for the vertical asymptote, let me switch color. That one compares the denominator. What would make my denominator equal to 0 is going to be my vertical asymptote. So right here, if x were 1 or negative 1, so if x equals 1 or x equals negative 1, I would have a vertical asymptote. Those are imaginary lines my graph will not touch. For horizontal, you just look at the degree. So the degree in the numerator is a 1 and the degree in the denominator is a 2. So if the degree in the denominator is larger, then it's automatically y equals 0 for the horizontal. All right, let's move on to example 2. There's nothing I can factor out of this denominator, and then there's nothing that will cancel. So once again, there are no holes for this example. For the vertical asymptote, you look at the denominator. What would make 2x plus 1 equal to 0? I'm just going to write it down here. So if 2x plus 1 equals 0, we could subtract 1, so 2x equals negative 1, and we could divide by 2, so we get x equals negative 1/2. So that is our vertical asymptote. So it's what would make the denominator equal to 0. Then the horizontal, you compare the degree in the numerator, which is a 1 in this case, to the denominator, which is a 1. So they're the same. So that's the kind where you pick out a over b. So y would equal 1 over 2. And then let's look at the third example. First, we want to factor out anything we can. So let's factor the numerator. And we can tell that this would cancel with the denominator and leave us with just x plus 1. So if x minus 1 cancels out, we have a hole at x equals 1. The vertical asymptote would then be looking at our denominator right here, but our denominator canceled out. So we actually have no vertical asymptote, and we are going to have no horizontal because the degree in the numerator is now larger than the degree in the denominator. All right, so let's look at a few examples of how to sketch the graph. Now for these examples, I've already taken the time to pick out the points of discontinuity, so we don't spend time on those. We just focus on the graph. So let me close these up real quick. And let me get the markers that match these colors so we can keep it all organized. So for example 1, we have the function f of x equals -5 over x plus 1. There are no holes. There's a vertical asymptote at x equals -1. So you want to draw an imaginary vertical line at x equals -1. And then the horizontal asymptote is at y equals 0, which is just the x-axis. Now to sketch your graph without a calculator, because you could certainly type this in and use your calculator to just help see where your graph goes. We're going to end up with branches is what we call them. So to figure out where these branches go, these little pieces of our graph, we can plug in values for x and figure out the y. And then we'll be able to tell if my little branch goes at the top or the bottom on this side, or the top or the bottom on that side, because it has to be one or the other. It can't be on the top and the bottom of this imaginary horizontal line. So I'm going to choose a value over here, like -2, for example, for my x. I'm going to plug it in. So -5 divided by -2 plus 1. -2 plus 1 is -1. So that's -2, 5. So if the point -2, 5 is on my graph, -2, 1, 2, 3, 4, 5, I know that my graph is over here in this area. That's a rough sketch. Please forgive me. Then I'm going to check one over here. Like I could check 0 for x. That's an easy one to check right there. So if I have 0 for x, I get -5 over 0 plus 1, which is 1. So that's 0, -5. So if I go 0, 1, 2, 3, 4, 5, then I know my graph is also in that little area. And again, you can use your calculator to check that, but that helps you to graph it by hand in case you don't have a fancy calculator. Let's look at another one. I've already factored out this one, so that if you have the factored form, you can see that the x's would cancel out right here. That gives us a hole at x equals 0. We have a vertical asymptote. We look at the simplified form for that after you've canceled out that hole at x equals 3. And then the horizontal asymptote would be at y equals 1 because your degree was the same and you had a 1 divided by a 1 right there. So now let's sketch the graph. If we're going to put the hole in our graph last. I'm going to graph the vertical asymptote at x equals 3. So an imaginary line at x equals 3. The horizontal was at y equals 1. And then we can pick out some values to figure out where the rest of our little branches go. So again, our graph would have to be in the top or the bottom here, or the top or the bottom over here. So I'm going to plug in 0. That's always an easy one to use. And you can just plug it into the simplified form. So if we just look at 0 minus 1, that's -1, over 0 minus 3 is -3. That's 0 and positive 1/3. So if I know 0 and positive 1/3, then that would be right there, underneath the y equals 1 asymptote. So then I know I'm going to need to sketch this one, not touching the asymptotes, but a little branch in that area of my graph. And then I'm going to plug in x equals 1, 2, 3, let's say 4. So 4 minus 1 is 3, and 4 minus 3 is 1. So I have the point 4, 3. So if I go to 4, 3, it's about right there, then I know my graph is going to be in this area. So make it nice and neat for your notes in your notebook. And there's one more I want to look at. But remember, you can also use your calculator to help you with this part. What's good is to graph the original function and make sure you put your numerator and denominator in parentheses if you're going to use your calculator for this part. Let's just look at one more. Again, I've already picked out the points of discontinuity. Oh, wait a minute, that reminds me. 1 second. We had a hole over here. The hole was at x equals 0. I almost forgot. If the hole is at x equals 0, you go to that spot and you just put a little hole right there on, like for me, it's the blue part of my graph because it's where the branch was. All right, so now let's look at one more example. But we put the holes in there last. But don't forget that one like I did. So let's look at this one. If we have a vertical asymptote at x equals -2, we draw an imaginary vertical line at x equals -2. There's a horizontal line at y equals 1/2. And we can see that the reason why it was x equals -2, let's go back for a minute, is I've already factored it out. So I took the original function, I factored the numerator into x plus 1, x minus 1. The denominator, I took out a greatest common factor of 2, and then I had x minus 1, x plus 2 left over. And so there was a hole at x equals 1 because x minus 1 canceled out. So that's where I got the hole at x equals 1. And then the simplified form gives me x plus 2 is my denominator. So that's where the vertical asymptote came from. X would have to equal -2 for my denominator to equal 0. And then the horizontal asymptote is 1/2 because the degree was the same in the numerator and the denominator. All right, I got a little ahead of myself. Now, let's check two values. That's all we need for this one so that we can see if our graph is at the top or the bottom, top or the bottom. So if I go -1, 2, 3, let's say x equals -3, and I plug it in the simplified form, I would have -3 plus 1 in the numerator is -2 divided by 2 times -3 plus 2. So let's see, that would be -3, and then -2 over -3 plus 2 is -1. 2 times -1 is -2. So -3, 1. So -3, 1 is about right there. Then let's check 0. If I plug in 0 into my simplified form, I have 1/2 times 0 plus 2. So 2 times 2 is 4, which gives me 0, 1/4. So at 0, 1/4, that's below 1/2 right there. So we can sketch our graph. We know it's going to be in this general area and in that general area. But make yours curve a little more and not look like such a right angle. And then we needed to put in our hole this time. So if x equals 1 is our hole, we need to go to x equals 1 and right on that blue line put a hole, just a little circle where the graph does not exist. All right, so that's all for now on graphing rational functions.